The edge of everything you can see is not a wall. It is not a boundary line someone drew on a map, not a place where space runs out, not the point where matter ends and emptiness begins. It is simply the distance light has been able to travel since the universe became transparent to it, a horizon defined not by what exists out there, but by how much time has passed since the beginning. And the single most disorienting fact in all of cosmology is this: beyond that horizon, the universe almost certainly continues. Not in a vague, speculative, hand-waving way, in a direct, mathematically motivated, observationally supported way. The universe beyond what you can see is almost certainly vast beyond any concept of vastness you currently hold. And if you could somehow travel past the edge of what is visible, what you would find there would not, at first, seem strange at all. If you enjoy videos that take the most extreme questions physics allows and follow them, honestly and precisely, wherever they lead, into the structure of space itself, into the mathematics of the very large, into the philosophy that lives at the boundary between what we know and what we cannot know, I'd genuinely appreciate it if you hit that like button and subscribe. It helps more than you know. Now, settle in, get yourself nice and comfortable. Let's begin. The most common misconception about the observable universe is that it describes the size of the universe. When people hear observable universe, imagine it the way you might imagine a fishbowl, a finite container, with walls beyond which there is nothing. The observable universe is 93 billion light-years in diameter, and people hear that number and think, that is the universe. Everything that exists fits inside that sphere. Beyond it is the void. That framing is wrong. Not approximately wrong. Not wrong in the way that oversimplifications are wrong. Categorically, fundamentally, architecturally wrong. The observable universe is not the universe. It is our view of the universe, the portion of it from which light has had time to reach us in the 13.8 billion years since the Big Bang. The universe itself is under no obligation to stop where our vision stops, and every piece of evidence we have suggests it does not. The correct framework, the one you need to carry through everything that follows, is this. Think of yourself standing in the middle of an enormous fog. The fog has no edges. It extends in every direction, as far as the fog goes, which is very far indeed. But your vision is limited. You can see only as far as the light can reach you before it is swallowed by the fog. There is a sphere around you, your personal horizon, beyond which you cannot see. But the fog beyond your horizon is still there. Other observers, standing in different positions, have their own horizons, their own spheres of visibility. Your spheres overlap in their outer regions. Beyond both your horizons, the fog continues. No one knows how far, but the fog is real, and it does not end where your vision ends. The observable universe is your sphere in the fog. The universe is the fog itself. Carry that framework. We will return to it constantly, because everything else we discuss is a deepening of that image, a precise accounting of what the fog is made of, how far it extends, what it contains, and what it would mean to cross your own horizon into the part of it you have never seen. To understand what lies beyond the observable universe and what it would mean to travel there, you first need to understand with precision why we cannot see it. Not because anything is blocking the view, not because space is opaque, but because of a physical limit that is, in its own way, one of the most profound ideas in all of science. The finite speed of light combined with the finite age of the universe, produces a horizon. And unlike most horizons we encounter in ordinary life, the horizon at sea, the horizon over a hill, the horizon formed by the curve of the Earth, this horizon is not a property of your position or your elevation. It is a property of time itself. Every object you see when you look at the sky, you see as it was in the past, not as it is now. The moon, as you see it, is a little over a second in the past. The sun is 8 minutes in the past. The nearest star beyond our sun, Proxima Centauri, is 4 years and 3 months in the past, meaning the light you see from it tonight left that star in early 2022, when the world was a specific and different place, and has been travelling through interstellar space ever since, entirely indifferent to everything that has happened on Earth in the intervening years. The Andromeda Galaxy, the nearest large galaxy, is about 2.5 million years in the past. The light arriving at your eye tonight left Andromeda when the first stone tools were being knapped by early humans on the African savanna, when the genus Homo was young and the grasslands were full of creatures we would not recognize as our ancestors, but who were nonetheless our ancestors. That light has been crossing the intergalactic void, 2.5 million light years of near-perfect emptiness, since before Homo sapiens was a species. It has been travelling longer than the entire history of anatomically modern humanity, longer than the entirety of recorded history multiplied by thousands, through a void so empty that if you removed every atom from it, there would be almost nothing left to remove. The most distant galaxies we observe with powerful telescopes, instruments like the James Webb Space Telescope, which began scientific operations in 2022 and has detected galaxies whose light was emitted when the universe was less than 300 million years old, are seen as they were 13 billion or more years ago when the universe was in its earliest infancy, when the first stars were forming from the pristine hydrogen and helium left over from the Big Bang. When the chemical elements heavier than lithium did not yet exist anywhere in the cosmos except in the interiors of those first-generation stars, the so-called population 3 stars, massive and hot and extraordinarily short-lived, which lived for only a few million years before dying in supernovae that seeded the universe with the first heavy elements. You are not looking at those distant galaxies as they are now. You are looking at their deep past. Their present, what they look like 13 billion years after they emitted the light reaching your telescope tonight, is permanently unknown, because the light from their present has not yet arrived. And then there is the cosmic microwave background radiation, the oldest light in the universe, the relic glow of the Big Bang itself. The photons that were released when the universe first became transparent to electromagnetic radiation, approximately 380,000 years after the Big Bang. At that moment, called recombination, the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before recombination, the universe was a hot, dense plasma through which light scattered endlessly, the way sunlight scatters off clouds, making the daytime sky bright without revealing the sun itself. After recombination, the universe became transparent. Photons could travel freely through space, and they have been doing so ever since. Those photons are the cosmic microwave background. They were emitted as visible and near-infrared light, but the 13.8 billion years of cosmic expansion since their release has stretched their wavelengths by a factor of roughly 1,100, pushing them into the microwave part of the electromagnetic spectrum. They arrive at our detectors as a perfectly uniform bath of radiation at a temperature of 2.725 degrees. 2.725 degrees above absolute zero, filling the sky in every direction. The CMB is the oldest observable thing in the universe. It is the visual horizon. Beyond the CMB, in terms of look-back time, we cannot see using electromagnetic radiation. Not because space ends there, because the universe before recombination was opaque, a wall of scattering plasma through which no photon could travel far enough to reach us. Everything that happened in the first 380,000 years of the universe's history is hidden behind the CMB. We can probe it using gravitational waves and neutrinos, which interact so weakly with matter that even the early plasma was largely transparent to them. But these probes are extraordinarily difficult to detect and currently remain beyond our observational reach for the early universe. The CMB is the limit of our electromagnetic vision. But this is a temporal limit, not a spatial one. The matter that emitted the cosmic microwave background 13.8 billion years ago has not stopped existing. It has continued to evolve, forming galaxies, forming stars, burning through stellar generations, scattering heavy elements, building complexity in the billions of years since those photons were released. It is out there now, in the present moment of cosmic time, separated from us not by the 13.8 billion light-years you might naively expect from the look-back time, but by roughly 46 billion light-years. The universe has been expanding while the light was travelling toward us, carrying the matter that emitted those photons ever further away. The observable universe is 93 billion light-years in diameter, 46 billion in every direction, because the matter that emitted the oldest visible light is now that far away, carried there by the expansion of space over 13.8 billion years. And beyond 46 billion light-years in any direction, the universe continues. We simply cannot see it. Now let us talk about the expansion of the universe itself, because this is where most intuitions fail most completely. In 1929, Edwin Hubble published what is arguably the most consequential paper in the history of cosmology. Working at the Mount Wilson Observatory in California, using the 100-inch Hooker telescope, the largest telescope in the world at the time, Hubble had been measuring the distances to what were then called spiral nebulae, fizzy patches of light whose true nature was disputed. Were they clouds of gas within the Milky Way, or separate galaxies at enormous distances? The question had been the subject of the Great Debate of 1920, in which Harlow Shapley argued for a compact Milky Way containing all the nebulae, and Heber Curtis argued for a vast universe of separate island universes. Hubble settled the debate with measurements of Cepheid variable stars, stars whose intrinsic brightness is linked to their pulsation period, providing a reliable distance indicator in several nebulae. The answer was unambiguous. The spiral nebulae were millions of light-years away, far beyond any possible extent of the Milky Way. They were separate galaxies. The universe was enormous. But the discovery that changed cosmology forever was not the distance measurements alone. It was what happened when Hubble correlated those distances with the redshifts of the galaxies, the shifts of their spectral lines toward longer, redder wavelengths, which had been measured for many nebulae by Vesto Slipher at Lowell Observatory in the preceding years. Hubble found a linear relationship. More distant galaxies had larger redshifts, in proportion to their distance. The recession speed was proportional to distance. The universe was not static, it was expanding, and not just locally. Everywhere Hubble could measure, the galaxies were receding, and the recession scaled with distance in exactly the way you would expect if the entire fabric of space were expanding uniformly, carrying the galaxies with it. The bread-go analogy, imperfect as all analogies are, captures the essential point. Imagine dough filled with raisins rising in an oven. As the dough expands, every raisin moves away from every other raisin. From any one raisin's perspective, all the other raisins are receding, and the more distant ones are receding faster because there is more expanding dough between them. There is no center of the expansion from any raisin's point of view. Every raisin is equally justified in considering itself the center. The raisins are not moving through the dough. The dough is expanding, carrying the raisins with it. The galaxies are the raisins. Space is the dough. The Hubble recession is the expansion of the dough, not the motion of the raisins through it. This distinction is not pedantic. It is the single most important physical fact for understanding the observable universe and what lies beyond it. In special relativity, the speed of light is the maximum speed at which objects can move through space. Nothing material can be accelerated to or beyond light speed through the medium of space. But the expansion of space itself, the growth of the metric, the stretching of the dough, is not limited by this constraint. There is no law in general relativity that limits how fast space can expand. Space can expand at any rate, carrying galaxies with it, without those galaxies moving through space faster than light. This is why there are galaxies in the observable universe that are receding from us at many times the speed of light even now, and whose light nonetheless reaches us, because they were closer in the past when their light was emitted. And the light has been slowly crossing the expanding space between us ever since. And this is why there are galaxies beyond the cosmic event horizon, the sphere at approximately 16 billion light-years, from which no light will ever reach us, because the space between us and those galaxies is expanding fast enough that even light emitted toward us today will never make net progress in our direction. The space is winning the race. Those galaxies will never be seen, even in principle, even given infinite future time. They are permanently beyond our causal reach. Light from us will never reach them either. We and they are in permanent causal isolation, not because of anything blocking the light, but because the space between us is actively, relentlessly, permanently expanding, faster than light can cross it. The cosmic event horizon at 16 billion light-years and the observable universe at 93 billion light-years are different things for an important reason. The event horizon has changed over time. For most of the universe's history, the expansion was decelerating. Gravity was slowing things down. The event horizon was growing relative to the observable universe. And light from regions now beyond the event horizon was able to reach us in the past because those regions were within the light travel distance available at that earlier epoch. But approximately 5 billion years ago, a fundamental change occurred. The expansion of the universe stopped decelerating and started accelerating. The universe began expanding faster and faster. This acceleration is attributed to dark energy, a component of the universe's energy density that does not dilute as the universe expands, unlike matter and radiation, whose densities decline as the volume grows. In the standard cosmological model, dark energy comprises roughly 68% of the total energy content of the universe today. It is the dominant component, and it is causing the event horizon to shrink in co-moving terms. The universe is progressively cutting off more and more of itself from our causal reach as the accelerating expansion separates us from more and more galaxies faster than signals can cross. This has a profound implication for the far future. Observers in 1 trillion years, if any exist, will see a vastly smaller observable universe than we do. The galaxies of the local group our local gravitational neighborhood, which includes the Milky Way, Andromeda, the Triangulum Galaxy, and about 50 other smaller galaxies bound together by gravity, will remain. They will eventually merge into one large elliptical galaxy. But all other galaxies will have been redshifted beyond detection, their light stretched to wavelengths too long to detect, their recessional velocities too large for any signal to overcome. Future observers will see only their local gravitational island in a vast and apparently empty universe. They will have no evidence that other galaxies ever existed. The CMB will have been redshifted from microwaves to radio waves and eventually to wavelengths longer than the observable universe itself, undetectable. The evidence for the Big Bang, for the cosmic web, for the structure we see, all of it will have been redshifted into invisibility. A civilization arising in the far future, if such a thing is possible, would look out at an apparently static, isolated galaxy in an apparently empty universe, and might conclude, incorrectly but understandably, that the universe was small and fixed and ancient. We live in a privileged era, early enough that the evidence of the universe's origin and structure is still visible, before the accelerating expansion erases the record. This is not a digression, it is context. It tells you what the observable universe is, how it got its current size, why it has the horizon it has, and what forces are continuously reshaping it. Now you need one more piece of foundation before we begin the journey: inflation, and what it implies about what lies beyond. In 1980, physicist Alan Guth, then at Cornell, proposed that the very early universe, in the first unimaginably brief interval after the Big Bang, between roughly 10⁻³ seconds and 10⁻³ seconds, underwent a period of exponential expansion, so rapid that it utterly dwarfs anything that has happened since. During this period, called cosmic inflation, the universe doubled in size approximately 60 to 100 times in an interval shorter than any unit of time that has a name. The universe expanded by a factor of at least 10 squared, 26 zeros, in perhaps 10⁻³ seconds. To put that in a human reference frame, if you expanded a single proton by the same factor, it would become larger than the observable universe. What was a region smaller than a proton became a region the size of a grapefruit, and what was a grapefruit would, if inflation had continued, have become something vastly larger than the observable universe many times over. Inflation was not invented as an arbitrary addition to cosmology. It was proposed to solve specific, concrete problems that the standard Big Bang model, without inflation, could not explain. The horizon problem, the cosmic microwave background, is extraordinarily uniform in temperature across the entire sky, variations of only 1 part in 100,000. But in the standard Big Bang without inflation, the patches of the early universe that emitted the CMB in opposite directions of the sky, the patch that emitted the CMB you see in the north and the patch that emitted the CMB you see in the south, had never been in causal contact with each other by the time they emitted those photons. Not even close. Light simply had not had enough time to travel between them. And yet, they are at the same temperature to 1 part in 100,000. How? Random chance is not a plausible answer. The probability that two regions with no causal connection would independently arrive at the same temperature to 1 part in 100,000 is vanishingly small. And the CMB shows this uniformity across all pairs of opposite sky patches, not just one pair. Inflation solves this. Before inflation, the entire region that would become our observable universe was a tiny patch, small enough to have been in causal contact and to have thermalized, reach the same temperature through normal thermal processes. Then inflation expanded that patch by a factor of at least 10 squared, preserving the temperature uniformity while stretching that tiny causally connected patch into a region larger than the observable universe. The uniformity of the CMB is not a coincidence. It is the relic of a pre-inflationary era, when the universe was small enough to communicate. The flatness problem, as we discussed, the geometry of the universe is extremely close to flat, within 0.5% of the critical density required for perfect Euclidean flatness. But in the standard Big Bang without inflation, this flatness is an extraordinarily fine-tuned initial condition. Any deviation from perfect flatness in the early universe grows over time, amplified by the expansion. For the universe to still be within 0.5% of flatness after 13.8 billion years, the initial density would have had to be within 1 part in 10 to the power of 6, 0 of the critical density, at almost inconceivable precision. Inflation solves this elegantly. Exponential expansion flattens the spatial geometry in the same way that inflating a balloon flattens its surface. No matter what the initial curvature was, inflation stretches it away, leaving the observable universe as flat as the surface of a balloon, inflated to the size of a continent. The flatness is not a fine-tuned initial condition. It is the inevitable result of exponential expansion. The monopole problem, ground unified theories of particle physics, the theoretical frameworks that attempt to unify the strong, weak, and electromagnetic forces, predict the production of magnetic monopoles in the early universe. Magnetic monopoles are hypothetical particles carrying a single magnetic pole, only north or northerly south, unlike the magnets we know, which always have both poles. Grand unified theories predict that monopoles should have been produced in enormous quantities in the hot early universe, in densities sufficient to dominate the energy density of the cosmos and prevent the formation of galaxies and stars. We observe no magnetic monopoles. Inflation dilutes them to unmeasurably low densities by expanding the universe by such an enormous factor that any monopoles produced before inflation end up spread across a volume so vast that essentially none end up in any region the size of the black. Observable universe. Inflation works. It solves multiple independent problems with a single physical mechanism. And the predictions it makes about the observable universe, particularly its predictions about the statistical properties of the CMB fluctuations, which arise from quantum fluctuations in the inflaton field that were stretched to cosmic scales by the exponential expansion, have been confirmed by the WMAP satellite and the Planck satellite with extraordinary precision. The spectrum of CMB temperature fluctuations, how the amplitude of the fluctuations varies with angular scale, matches the predictions of the simplest inflationary models at the percent level or better. The fluctuations are nearly scale invariant, as inflation predicts. They are nearly Gaussian, as inflation predicts. The slight deviations from perfect scale invariance, the spectral tilt, match the predictions of single-field slow-roll inflationary models at high precision. Inflation is not a peripheral speculation. It is the best supported theory of the early universe we have. And inflation has a consequence for what lies beyond the observable universe that is more important than any of its solutions to the horizon and flatness and monopole problems. If inflation happened at all, it almost certainly happened throughout a region vastly larger than our observable universe. The inflaton field that drove inflation was present throughout the primordial cosmos, and the exponential expansion it drove stretched that primordial cosmos into something whose scale is almost impossible to express in ordinary terms. The region of space that became our observable universe was before inflation a tiny patch. Inflation stretched it into a region with a radius of at least 10 squared light years, a 10 followed by 23 zeros, compared to the 46 billion light year radius of our observable universe. And that estimate of 10 squared 1023 light years is a conservative lower bound. Some inflationary models predict a factor of expansion vastly larger than 10 squared 1006, which would imply a post-inflationary universe whose radius exceeds 10,450 light years or more. Our observable universe, 93 billion light years across, containing 2 trillion galaxies, more stars than grains of sand on all of Earth beaches, is, in this picture, a microscopic patch of a vastly larger inflated cosmos. All of it filled with the same kinds of matter, all of it governed by the same laws of physics, all of it invisible to us because the light from most of it has not had time to reach us. This is the first answer to what lies beyond the observable universe. More of the same. More inflated cosmos. More large-scale structure. More galaxies and stars and chemistry and whatever else physics produces when given enough matter and time. The cosmological principle, the hypothesis that the universe is homogeneous and isotropic on large scales, extends beyond the observable horizon by the best understanding we have of the physics that produced it. The inflation that made our observable universe uniform made the larger inflated region equally uniform. The same quantum fluctuations that seeded the structure in our observable region seeded structure throughout the entire inflated space. Beyond the edge of what you can see, the universe continues as if the edge were not there, because for the universe, it is not. The numbers implied by this are extraordinary. Our observable universe contains approximately 2 by 10 squared stars, 2 followed by 23 zeros. If the post-inflationary universe has a radius of at least 10 squared light years, its volume is at least 10 to the power of 6 times larger than the observable universe's volume, and it contains at least 10 to the power of 9 times as many galaxies and stars. These are not quantities that human intuition can process. They are not merely large numbers. They are large in a way that makes the difference between a human lifetime and the age of the universe seem trivial. By comparison, 200 million light years, the distance to the Shapley concentration, one of the most impressive structures in the observable universe, is to the radius of the post-inflationary universe as a single hydrogen atom is to the diameter of Earth. The post-inflationary universe, if inflation is correct, is genuinely, irreducibly, qualitatively vast in a way that the word vast cannot adequately convey. Now, the journey itself. Imagine that you were granted something physics does not permit, but imagination does. A ship capable of traversing any distance in any amount of time you choose. Not a warp drive constrained by the equations of general relativity. Not a wormhole whose throat you must locate and whose stability you must maintain. Simply a vessel that moves. You point it in a direction, away from everything you know, past the farthest galaxy you can see, past the region of space from which the cosmic microwave background was emitted, out beyond the limits of the observable universe, and you go. What do you experience? The first thing to understand, and this is the disorientation at the heart of the whole question, is that the journey through the observable universe and beyond does not feel like a journey toward an edge. There is no edge. There is no wall you approach and then pass through. There is no change in the quality of space, no moment at which the texture of reality shifts from the familiar to the alien. The observable universe is not defined by what is out there. It is defined by your position in time and by the finite speed of light. As you travel outward, your observable universe travels with you. The sphere of what is visible expands in the direction you're heading, because photons that could never reach your original position can now reach you in your new position, and contracts somewhat behind you in the region you've moved away from. The horizon is personal. It belongs to the observer, not to space. Every point in space has its own observable universe, its own sphere of visibility, its own CMB shell, its own event horizon. When you move to a new position, you acquire a new observable universe. The galaxies that were previously beyond your horizon and invisible to you are now, some of them, within your new horizon. The galaxies you left behind haven't vanished. They are still there, still emitting light, still evolving, but they are now slightly further from your new position, slightly more redshifted, slightly closer to the edge of your new horizon. And the galaxies in the direction you travelled? They have come slightly closer, their light slightly less redshifted, their past slightly more recent in the photons reaching you. You do not cross the boundary of the observable universe. You carry the boundary with you. This is the first great conceptual shift you must make. The journey beyond the observable universe is not a journey to a special place. Every place is inside someone's observable universe. Every cubic meter of space is, from its own perspective, the center of a sphere of visibility 93 billion light years in radius. The universe does not have a center or an edge in the spatial sense. It has centers only in the observer-dependent sense, and every point is the center of its own observable sphere. When you travel beyond your current horizon, you're not entering a different kind of space. You are entering space that is identical in its fundamental properties to the space you left, but which has a different history of what light has had time to reach it, and from whose perspective the center of the cosmos is located somewhere slightly different from where you started. Now, let us be more concrete. Let us actually make the journey, step by step, pausing at each threshold to describe what you would see and what it would mean. The Milky Way is still visible behind you, though it is shifted. The light you see from it is ancient. It left the galaxy long before you did, because you travelled faster than light. But the galaxy itself has continued to evolve in your absence. The Milky Way you see is not the one you left. It is a ghost of it, a billion years younger, an image of what it looked like when the light now reaching you was emitted. The Andromeda merger, if it has occurred in your future, has not yet occurred in the Milky Way you're seeing now. You're watching the image of the galaxy from before the event. Ahead of you, the large-scale structure of the universe is becoming visible in a way you couldn't appreciate from within the Milky Way. The cosmic web, the filaments of dark matter and ordinary matter, along which galaxies are threaded like beads on an invisible wire, is apparent to your instruments. You can see great walls of galaxies stretching across hundreds of millions of light years, separating vast voids that are almost completely empty. The Sloan Great Wall. The Hercules Corona Borealis Great Wall, the largest known structure in the observable universe, stretching across 10 billion light-years in a band that spans a substantial fraction of the entire observable sphere. These are not solid objects. They are statistical concentrations, regions where the density of matter is slightly higher than the average, producing filaments and sheets and knots of galaxy clusters along the gravitational skeleton of the cosmic web, with enormous underdense voids between them. You navigate between the filaments, through the voids, which are not truly empty, but contain a sparse scattering of galaxies that formed in isolation, far from the density peaks that birthed the rich clusters and galaxy groups. The voids are eerie in a way that is hard to convey. Enormous regions of space, hundreds of millions of light years across, containing almost nothing. The Butes void, which is relatively nearby in cosmological terms, at a distance of about 700 million light years, and which spans some 330 million light years, contains roughly 60 galaxies where you would expect thousands. Inside the Butes void, if you were stationed there, you would look out into intergalactic space and see almost nothing in most directions, just the distant walls of the void, hundreds of millions of light years away, dimly luminous with the galaxies that define its boundaries. The loneliness of the void is a physical reality, not a metaphor. The universe has structured itself in a way that produces regions of genuine cosmic emptiness, islands of near-nothingness vast beyond comprehension, between the filaments and walls where all the luminous matter has gathered. At 1 billion light years, you are still well within the observable universe. You have barely begun. The horizon is still 46 billion light years away in the direction you came from, and, depending on your speed relative to the expansion, roughly as far ahead. But already, the universe looks different from any vantage point you've ever occupied. Different not in its fundamental character, but in its vistas. The Milky Way, the local group, the Virgo supercluster, all of it is behind you now, reduced to a point of light in the structure of the cosmic web, indistinguishable from the thousands of other galaxy clusters in your backward field of view. Now you are approaching the practical limits of what our deepest telescopes can observe. The galaxies ahead of you, in the direction of your travel, are beginning to look different, not because they are intrinsically different, but because you are seeing them as they were closer to their formation. The galaxy sizes are smaller. The morphologies are different, more irregular, more chaotic, less organized into the grand spiral patterns and elliptical forms of the modern universe. You are looking at the universe in its adolescence, when the cosmic web was still settling into its final form, when mergers between galaxies were more frequent, when quasars, the intensely luminous cores of galaxies in which supermassive black holes were devouring matter at prodigious rates, were more common and more brilliant. The universe ahead of you is younger, hotter in some respects, more energetic, more active. Behind you, the Milky Way is now 10 billion light years away. The light you see from it left the galaxy 10 billion years ago, long before the solar system formed, long before the Earth existed, long before any of the atoms that make up your body were forged in stars. The Milky Way you see behind you is an infant, a young, irregular, gas-rich galaxy still assembling itself, not yet the graceful spiral structure of the mature galaxy you left. You are watching your own home in the deep past, seeing it as it was when no life could have existed there. The galaxy you came from does not yet contain a star that will become the sun. The galaxy you're watching will build one in another 4 billion years. That fact is simultaneously obvious and dizzying. At 10 billion light years, you can detect the acceleration of the cosmic expansion directly in your instruments. The rate at which distant galaxies are receding from you, in all directions, is measurably different from the rate at which they were receding 1 billion years ago. The dark energy that dominates the energy budget of the universe is not static in its effects over cosmic time. Its influence on the expansion rate evolves. And from your vantage point, you can trace that evolution with the redshifts of galaxies at different distances, watching the expansion history of the universe play out across your instruments like a graph unfolding in real time. Here too, the first hints of something philosophically vertiginous begin to emerge. The realization that the universe's history is not just a timeline that happened, it is, in a deep sense, still happening. Everything that has ever occurred in the cosmos is, somewhere in the structure of space, still visible, its light still travelling, still encoding the information of those ancient events, still arriving at new observers in new positions. The past is not gone. It is distributed through the cosmos as light, arriving at different times at different places, creating a kind of eternal record that will persist, in principle, forever, though stretched to ever longer wavelengths, ever closer to undetectability. As the expansion continues, you approach the region from which the cosmic microwave background was emitted. Not the CMB radiation itself. Those photons left this region 13.8 billion years ago and are now passing through your original position, far behind you. What you approach is the matter that emitted those photons. The stuff, the hydrogen and helium plasma that was recombining into neutral atoms 380,000 years after the Big Bang, releasing the photons that became the CMB. That matter has, in the 13.8 billion years since recombination, formed galaxies and stars and everything else the universe contains. It is here, ahead of you, and you are approaching it. What do you see? More galaxies, more large-scale structure, more cosmic web. The matter that was at the recombination surface is not special matter. It is the same kind of matter that forms everything else in the universe. It has followed the same laws of physics, assembled itself into the same kinds of structures, produced the same kinds of stars and galaxies. From its own perspective, it is at the centre of its own observable universe. The cosmic microwave background that it sees is different from the one you see. It was emitted by matter now far away in its own sky, matter that from your perspective is well within your own observable universe. As you cross what was, from your starting point, the edge of the observable universe, nothing happens. There is no wall. There is no change in the quality of space. There is no sudden darkness or emptiness or shift in the physical laws. The galaxies continues, the large-scale structure continues, the cosmic web continues, the void continues, the filaments and sheets and knots of the gravitational skeleton continue. The universe, as experienced from this new vantage point, is indistinguishable from the universe you left. This is the first and most fundamental answer to the question of what lies beyond the observable universe, the same thing that lies within it. Space, matter, structure, physics. The boundary was never a boundary in any physical sense. It was always a horizon, a limit of vision, not a limit of existence. The observable universe you now carry with you, centered on your new position, extending 46 billion light-years in every direction, contains billions of galaxies you have never seen and could never have seen from Earth. Their light, aimed in your direction, is still crossing the vast distances toward you. Some of those galaxies contain stars. Some of those stars have planets. Some of those planets may have conditions amenable to chemistry. The universe does not care whether you could see those places from where you started. It produced them according to the same physics that produced the places you could see. The numbers stop meaning much to direct intuition, but the physics remains clear and consistent. The universe continues. The large-scale structure continues. Though it has its own characteristic scale, the pattern of filaments in voids repeats at roughly the same statistical scale regardless of where you are. Because the quantum fluctuations that seeded all structure were produced during inflation with a nearly scale-invariant spectrum, meaning the same pattern of density perturbations was laid down across all scales, producing the same statistical fingerprint of the cosmic web everywhere you go. But here, at truly enormous distances from your starting point, distances that dwarf the observable universe, the way the observable universe dwarfs an atom, a subtlety emerges that even most physicists don't spend much time contemplating. You are now so far from your origin that the two of you and whatever observer might remain at your starting point, are in permanent causal isolation. Not the causal isolation imposed by the cosmic event horizon, which merely says that no future signals can connect you. A deeper isolation, even if signals were sent in the past, from back when you were closer, those signals are still crossing the expanding space between you, and the space is expanding faster than the signals travel. There is no physical process by which information can pass between your current position and your point of origin. Not now, not ever. You are not just beyond the observable universe of Earth. You are beyond the reachable universe of Earth. You are in a region that has been in causal isolation from Earth for long enough that no event at your location has ever been able to affect any event at Earth's location, and no event at Earth has ever been able to affect your location. In the language of general relativity, your current position and Earth are in non-overlapping light cones. The two regions share a common origin. The Big Bang produced both, but no causal influence has ever passed between them, and none ever will. And yet, the physics is the same. This is the cosmological principle in its most powerful and most vertiginous form. The universe is governed by the same laws everywhere, not because everything is in causal contact, but because those laws were set at the Big Bang and propagated with inflation into every region simultaneously. Every region of the universe, no matter how causally isolated from every other, plays by the same rules. The constants of nature, the fine structure constant, the gravitational constant, the speed of light, the mass of the electron, the strength of the strong nuclear force, are, as far as we can determine, the same everywhere we can observe. And the extrapolation beyond the observable universe, justified by inflation, suggests that they are the same everywhere we cannot observe. Here is where the most important philosophical tension of this journey comes into focus. We have been assuming throughout that the laws of physics and the constants of nature are truly universal, that they are the same in the regions beyond our observable universe as they are within it. This assumption is well supported for the post-inflationary universe we've been discussing. The physics of inflation predicts it. The uniformity of the CMB confirms the uniform conditions within the observable universe. And the extrapolation beyond is the most parsimonious one available. But there is a class of theories arising naturally from the physics of inflation itself, in which this assumption fails. In which the universe beyond the observable horizon does not have the same constants of nature, in which the laws of physics are different, not in their fundamental structure, but in the values of the parameters that define them. This class of theories goes by the name eternal inflation, and it is perhaps the most unsettling idea in all of modern cosmology. The inflaton field that drove the exponential expansion of the early universe was, according to quantum field theory, subject to quantum fluctuations. In most inflationary models, the field was slowly rolling downhill in its potential energy landscape, losing energy as it rolled, driving inflation as it did so, and eventually reaching the bottom of the potential, where inflation ended and the energy of the field was converted into the hot plasma of the standard Big Bang. This process happens throughout our local region of space, the region that became our observable universe, and the much larger post-inflationary cosmos we've been discussing. Inflation ended and the hot Big Bang began. But quantum fluctuations are random, and in a sufficiently large and long-lived inflationary field, quantum fluctuations occasionally push the field uphill in its potential rather than downhill. In those regions, inflation continues rather than ending. The field rolls back up, driven by its quantum nature, and the exponential expansion continues even as surrounding regions have long since transitioned to the standard hot Big Bang phase. These regions of continued inflation expand exponentially, becoming vastly larger than the regions that have already transitioned. Within them, the quantum fluctuations can again push the field to higher or lower values, with some patches transitioning to the hot Big Bang phase and others continuing to inflate. This process, once started, never stops. The regions of continued inflation expand so rapidly that even though they are constantly spawning patches that transition to the hot Big Bang phase, each of which becomes from the inside a vast post-inflationary universe, the inflating volume grows faster than the transitioning volume shrinks it. The inflating volume is eternal. It continues forever, producing an infinite number of post-inflationary universe patches, each separated from the others by inflating regions that will never be traversed. Each patch becomes what cosmologists call a cage. Bubble universe, a vast region of space in which inflation has ended, the hot Big Bang has occurred, and physics as we know it has unfolded. And here is the crucial step. The state in which the inflaton field finds itself when inflation ends, the specific value of the field at the bottom of its potential, determines the physical parameters of the universe that emerges from the transition. Different patches of the inflating background can transition at different field values, producing different effective vacuum energies, different particle masses, different coupling constants. In the language of string theory, which provides the most developed candidate for a fundamental theory underlying inflation, the landscape of possible vacuum states is enormous, perhaps 10 to the power of 550 distinct vacuum configurations, each corresponding to a different set of physical constants. Different bubble universes settle into different vacua with different physics. This is the multiverse, not the multiverse of science fiction, where parallel versions of you make different choices in different branches of quantum history. Multiverse is long, not the many worlds interpretation of quantum mechanics, in which the wave function of the universe branches with every measurement. This is a cosmological multiverse, physically distinct regions of space, each enormous in its own right, each with its own Big Bang, its own cosmic microwave background, its own large-scale structure, its own physics. They are separated not by any traversable barrier, but by eternally inflating space. No signal can cross from one bubble to another. No physical object can travel from one to another. They are, in the most rigorous physical sense, causally disconnected forever. What lies beyond our observable universe, in this picture, is not simply more of the same. It is more of the same for a while, the vast post-inflationary cosmos we've been discussing, with the same physics and the same kinds of galaxies and the same kinds of stars, stretching across distances that make the observable universe look microscopic. But eventually, that distance is so enormous that they make even the 10 squared light-year radius of the post-inflationary cosmos look small. You reach the boundary of our bubble universe. The edge of the region in which our inflaton field completed its transition, beyond that boundary, eternal inflation, the inflating background, the no man's land between bubble universes, expanding forever, never producing the conditions necessary for atoms or chemistry or stars. And beyond that, other bubbles, other universes, each with its own volume, potentially enormous, each with its own physics, each producing its own stars, or not, because a universe with even slightly different constants might not produce stars at all. A universe with a slightly larger cosmological constant would have expanded so rapidly after its Big Bang that matter never had time to clump into galaxies. A universe with a slightly different electron mass would have different chemistry, the atoms themselves would be different, the chemical bonds would have different energies. The molecules that constitute life, as we understand it, might not be stable. A universe with a slightly different strong nuclear force would not have stable carbon. The nucleus that is the backbone of biochemistry would not hold together. The range of possible physics is vast, and only a small fraction of it is compatible with the existence of complex structures of any kind. This observation led to one of the most controversial ideas in modern physics, the anthropic principle. If the constants of nature are not uniquely determined by some fundamental theory, but instead vary across the landscape of bubble universes in the multiverse, then there is a selection effect at work. We necessarily find ourselves in a universe whose constants are compatible with our existence, because in universes where the constants are incompatible with our existence, there are no observers to find themselves anywhere. This does not require that the constants be tuned by any agent. It merely requires that the space of possible universes be large enough that some fraction of it, however small, happens to have constants within the range compatible with observers, and that we are, inevitably, in that fraction. The anthropic principle is either a profound insight or a profound failure of physics, depending on whom you ask, and reasonable physicists disagree vigorously. Its proponents point out that it provides the first rational explanation for why the cosmological constant, which should, according to naive quantum field theory calculations, be 10 times larger than its observed value. A discrepancy, known as the cosmological constant problem, and often described as the worst prediction in the history of physics, is so small. In the landscape of bubble universes, the cosmological constant varies across many orders of magnitude. Only bubble universes with a small cosmological constant produce galaxies. All the rest are either torn apart by rapid expansion or collapse before structure can form. We necessarily live in one of the former. The small cosmological constant is an anthropic selection effect, not a fundamental law. Its critics argue that this reasoning is unfalsifiable, that a theory which predicts, in principle, every possible set of physical constants, with no way to check which prediction applies to any given universe, is not really a theory at all. It is a way of giving up on explanation. And there is a legitimate intellectual concern here. If the constants of nature are what they are, not because of any deep physical law, but merely because we happen to be in a bubble where they have these values, then there is nothing more to explain about them. nothing to derive, nothing to predict. The deepest questions of physics: why is the electron mass what it is? Why is the fine structure constant 137? Why is the cosmological constant so small? Become, in this picture, no more answerable than the question of why we were born in this particular country rather than another. The answer is, because we were, and no further explanation is forthcoming or necessary. The debate is not resolved. It may never be resolvable. The multiverse, predicted by eternal inflation, makes no testable predictions about our own observable universe that distinguish it from a universe that simply exists in isolation, without a multiverse. This is its deepest problem, not that it is wrong, but that it may be unverifiable in principle, making it a question for the philosophy of science as much as for science itself. But you are not on your ship to verify the multiverse. You are there to see it. And what you find, if eternal inflation is correct, and if you could somehow navigate the inflationary background, which physics does not permit, but imagination does, is a landscape of bubble universes, each enormous, each separated from the others by the eternally expanding, inflating medium, each governed by its own specific set of physical laws, some producing stars and galaxies, and perhaps life, others producing only a brief flash of hot plasma, followed by rapid dilution into emptiness, others collapsing before any structure forms. The bubble universes are distributed across the inflationary background in all directions, at unimaginable distances, and each one is a cosmos unto itself, complete, self-contained, governed by its own physics, carrying no knowledge of and no connection to any other. Let us step back from the journey for a moment and sit with the philosophical weight of what we've described. Because there is something at the intersection of infinity and physics that demands careful attention, and most popular treatments of cosmology skip past it far too quickly. If the universe, the full post-inflationary cosmos, not just our observable sphere, is spatially infinite, then it contains an infinite number of regions the size of our observable universe. An infinite number of Hubble volumes, each containing approximately 2 trillion galaxies and some 10 squared stars. In an infinite universe with the same physics throughout, every possible arrangement of matter that is physically possible will occur somewhere, not just once, infinitely often. This is not speculation, it is arithmetic. The number of distinct quantum states that a region the size of our observable universe can contain is vast but finite. It is bounded by the Bekenstein-Hawking entropy formula, which links the maximum information content of a region to the area of its boundary in Planck units. This number is enormous, something like 10 to the power of 10 123, but it is finite. In an infinite universe, every one of those states is realized an infinite number of times. There are, in an infinite spatially flat universe, an infinite number of regions identical to our observable universe, containing the same galaxies, the same stars, the same planets, the same arrangement of matter down to the quantum level. There are an infinite number of regions nearly identical to ours. There are an infinite number of regions containing Earth, containing you, but in which every detail of your life is slightly different, because the range of possible states allows for every variation. This is not the many worlds interpretation of quantum mechanics. This is simpler and more concrete. It is merely the implication of infinity combined with finite state space. In an infinite universe, the repetition is not a quantum phenomenon or a philosophical abstraction. It is as real as the repetition of, say, weather patterns. Give a finite system with finite states enough time or space, and it must repeat. The nearest copy of you in a flat, infinite post-inflationary universe is estimated to be at a distance of roughly 10 to the power of 10 squared meters. This number is so large that it cannot even be meaningfully compared to other large numbers. The observable universe is about 10,266 meters in radius. The distance to the nearest copy of you is, according to this calculation, 1 followed by 10 to the 29th zeros, a power tower of such height that writing it out would require more characters than there are atoms in the observable universe. Repeated a number of times that exceeds the total number of atoms in the observable universe. It is not a number that fits in any human framework. But in an infinite universe, it is a distance that is finite, and beyond it, by the mathematics of infinite universes and finite state spaces, there exists a region of space that is, to any physical measurement, identical to ours. What do we make of this? Philosophers have argued about it. Physicists have largely ignored it, because it makes no testable predictions. The nearest copy is so far beyond our observable horizon that no observation could ever confirm or deny its existence. But the logic is sound, and if the universe is truly spatially infinite, as the best measurements of its flatness suggest, then this conclusion, bizarre as it is, follows as a mathematical necessity. We have been speaking of a flat universe, a universe in which the geometry of space on large scales is Euclidean, in which parallel lines never converge or diverge, in which the angles of triangles sum to 180 degrees. This is what the measurements tell us. The universe appears to be spatially flat to within the precision of our best observations, which is currently about 0.5%. But flat to within 0.5% does not mean perfectly flat. And the question of whether the universe is exactly flat, or slightly positively curved, or slightly negatively curved, is one of the most consequential unresolved questions in cosmology, because the answer determines, among other things, whether the universe is finite or infinite. A positively curved universe, analogous to the surface of a sphere, but in 3 spatial dimensions, is finite and unbounded. It wraps around on itself. If you travel far enough in any direction, you return to your starting point, just as a ship, sailing in a straight line on the surface of a sphere, eventually returns to its port. The universe in this case has no edge, but it has a finite volume. It contains a finite number of galaxies, a finite number of stars, a finite number of possible quantum states. In a positively curved universe, there are no exact copies of you. The universe may be large, very large, but it is not infinite, and the arithmetic of infinite repetition does not apply. A perfectly flat universe is infinite. It extends in all directions without limit, never wrapping back on itself, never returning to its starting point. The arithmetic of copies applies at full force. A negatively curved universe, analogous to a saddle shape, but in 3 dimensions, is also, in the simplest case, infinite. It diverges rather than converging, with parallel lines spreading apart rather than meeting or maintaining their distance. It also, in the simplest case, implies infinite copies. The measurements say flat to within 0.5%. But that constraint allows for a positively curved universe whose radius of curvature is larger than the observable universe, in which case we would not be able to detect the curvature locally, just as the curvature of the Earth is not apparent from standing on a flat plane. If the universe is positively curved, but with a radius of curvature much larger than 46 billion light-years, it might contain 10 cubed, or 10^6, or 10^10 times the volume of the observable universe, enormous by any human standard, but finite, and eventually exhaustive of all its possible quantum states if you travel far enough. This question, the global topology of the universe, is one that current observations cannot definitively answer. The Planck satellite results constrain the curvature to be very small, implying a very large or infinite universe, but they cannot distinguish between the infinite case and the very large but finite case. Future observations with better measurements of the CMB at the largest angular scales might tighten the constraint further. But if the curvature is small enough, if the radius of curvature is much larger than the observable universe, we may never be able to determine observationally whether the universe is finite or infinite. The question may be, in practice, permanently unanswerable with electromagnetic observations. There is, however, a potential observational signature of vanity universe with curvature if the universe is small enough relative to the observable universe. We should be able to see ourselves, or rather, to see ancient light from our own galaxy, having made one or more complete circuits of the finite space. The sky in a small finite universe would contain a characteristic pattern of matched circles. In the CMB, pairs of rings in the sky where the same fluctuations appear twice, because the CMB photons from opposite directions are actually the same photons, having completed the circuit. Searches for this pattern in the WMP and Planck CMB data have not found convincing evidence of it, which constrains the minimum size of a finite universe and pushes it, if it exists, to dimensions much larger than the observable sphere. But the absence of detected matched circles does not rule out a finite universe. It merely constrains it to be large. There is one more direction to travel in this exploration, a direction that is not spatial, but temporal. We have been asking what lies beyond the observable universe in the sense of spatial distance. But there is also the question of what lies beyond the observable universe in the sense of temporal depth. What came before the Big Bang? What, if anything, existed before the universe we inhabit? The question is poorly posed in a strict physical sense, because the Big Bang is not an event that occurred at a particular moment in a pre-existing time. It is, in the standard cosmological model, the origin of time itself. General relativity describes the Big Bang as a singularity, a point at which the curvature of space-time becomes infinite, at which the density and temperature of matter diverge to infinity, and at which the classical equations of general relativity break down and cease to make predictions. The singularity is not a moment in time. It is the boundary of time, the edge of the domain within which the concept of before is defined. This is a genuine physical result, not a sleight of hand. The Penrose-Hawking singularity theorems, proved by Roger Penrose and Stephen Hawking in the 1960s and 1970s, demonstrate rigorously, under the assumption that general relativity is correct and that the universe satisfies reasonable energy conditions, that the universe must have begun in a singularity. The singularity is an inescapable feature of the mathematics of general relativity applied to the expanding universe. But general relativity is not the whole story. It is a classical theory, a theory that ignores quantum mechanics. And we know that quantum mechanics is fundamental. Every physical theory that ignores it is ultimately incomplete. The singularity of general relativity is a sign not that the universe actually started in a state of infinite density and temperature, but that general relativity breaks down before reaching that point and needs to be replaced by a quantum theory of gravity, a theory that combines quantum mechanics and general relativity in a fully consistent way. We do not yet have such a theory in a form that makes definitive predictions. String theory is the most developed candidate, but its application to cosmology, and specifically to the question of what happens near the Big Bang singularity, is not yet worked out to the point of yielding unambiguous answers. Several proposals exist for what a quantum theory of gravity might say about the Big Bang. The Hartle-Hawking no-boundary proposal, developed by James Hartle and Stephen Hawking in the early 1980s, suggests that the quantum state of the universe is such that the Big Bang singularity is replaced by a smooth, rounded space-time that has no boundary in the past. Time does not end at the Big Bang, it simply becomes ill-defined, in the same way that the concept of north of the North Pole is ill-defined. The universe, in this picture, simply exists. It has no beginning and no creator and no prior state. It is a closed space-time that is finite in both space and time, but has no boundary, no edge, no starting point that requires a prior explanation. The Vilenkin tunneling proposal, developed by Alexander Vilenkin, suggests instead that the universe tunneled into existence from nothing through a quantum process. Nothing, in this context, does not mean empty space. Empty space is something with its vacuum energy and its quantum fields and its geometric structure. It means a state in which there is no space, no time, no matter, no energy, nothing. Vilenkin's proposal suggests that quantum mechanics permits, indeed predicts, the spontaneous nucleation of universes from such a nothing, just as quantum tunneling allows a particle to pass through a potential barrier it classically could not surmount. The universe appeared not from nothing in the colloquial sense of an empty pre-existing void, but from a genuine absence of prior existence through a quantum process that did not require time to take place, because time itself was created in the process. Both proposals are mathematically sophisticated and physically motivated. Neither is currently testable in any direct sense. They differ in their predictions for the shape of the universe's quantum state, the wave function of the universe, and those differences, in principle, lead to different predictions for the spectrum of primordial perturbations and hence for the CMB. But the differences are subtle and current observations cannot distinguish between them. Future observations might. There is also the possibility that the Big Bang was not a beginning but a transition, a bounce, that the universe we inhabit was preceded by a contracting phase which reached a minimum volume and then began to expand. This idea, called the Big Bounce, is explored in loop quantum cosmology, an approach to quantum gravity that discretizes space-time at the Planck scale and finds that the singularity of general relativity is replaced in the quantum theory by a region of extreme but finite density through which the universe passes continuously. In this picture, the universe contracts to a minimum size, bounces, and then begins the expansion phase we observe. What preceded the bounce, whether there was a collapsing universe, and what preceded that, is a question loop quantum cosmology is beginning to address, with results that are intriguing but not yet definitive. And in the context of eternal inflation, the question of what came before takes on yet another character. If inflation is eternal in both directions, if the inflating background not only continues forever into the future, but also extends infinitely into the past, then there is no moment at which the universe began. The multiverse is eternal. Individual bubble universes have their own big bangs, their own beginnings, their own histories, but the inflationary background that spawns them has no beginning and no end, no creation event, no prior state from which it emerged. It simply is an eternal, ever-inflating medium in which bubble universes appear and vanish, like foam on an infinite ocean, each complete in itself, each a cosmos to those who might inhabit it, the whole representing a structure so large and so permanent that the concept of its creation loses coherence. Let us return for a moment from the grandest scales to the human scale, to the question of what it would actually be like to make this journey, not as an abstract exercise in cosmology, but as an experience. The journey from Earth to the edge of the observable universe and beyond would be, for most of it, profoundly quiet. Space is quiet. Space is dark between the galaxies. The cosmic microwave background is there, permeating all of space, filling every cubic centimetre with its 2.725 Kelvin radiation, but it is invisible to human eyes, and cold, and you would feel none of it as warmth. If voids are genuinely empty, the average density of matter in the universe is about 6 protons per cubic metre, and in the voids it is lower still, perhaps 1 proton per 5 cubic metres. Your ship is the densest thing for billions of light years in any direction when you are crossing the great voids of the cosmic web. You are an island of complexity in a sea of near-nothingness, so profound that the word emptiness cannot do it justice. The stars in the intergalactic medium are vanishingly rare. There are stars that were ejected from their home galaxies by gravitational interactions, hypervelocity stars, flung out by close encounters with black holes or by the disruption of binary systems, now drifting through intergalactic space in the voids between the filaments. You might pass one of these every few 100 million light years. It would be a sun, burning, alone in the void, no planets orbiting it that we know of, no other stars within millions of light years, just a single point of light in an otherwise featureless dark. The loneliness of such a star is a concept that no human mind, evolved on a world circling one of 200 billion stars in a dense and luminous galaxy, is equipped to fully grasp. And then the galaxies, seen from outside, are extraordinary. The Milky Way, your home, now impossibly far behind you, is a spiral galaxy about 100,000 light years across. From a distance of 1 million light years, it would appear as a glowing disk, faintly luminous, its spiral arms faintly distinguishable in the light of its 100 billion stars. From farther away, it shrinks to a point of light, then to a smear of photons, then to a red-shifted blur, then to nothing. All of human history, all of human civilization, all of the complexity and beauty and tragedy of life on Earth, all of it compressed into a point of light, then stretched by the expansion of space into a wavelength too long for any instrument to detect. That is what lies behind you. And ahead, more of the same, more points of light, more galaxies, each containing its own billions of stars, each with its own possibility of complexity, each receding or approaching according to its own cosmic motion. The whole fabric of the observable universe spread across the darkness like an impossibly sparse lattice, vast beyond all reckoning, and continuing, and continuing, and continuing. There is a particular kind of intellectual vertigo that good cosmology induces, and it is worth sitting in it for a moment, rather than resolving it too quickly into a tidy moral or a comfortable conclusion. The observable universe is vast beyond any ordinary concept of vastness. It contains 2 trillion galaxies, each containing on average perhaps 100 billion stars, and those stars have been burning for an average of several billion years, and the universe has been in existence for 13.8 billion years. The structures visible to us already strain comprehension. The Laniakea supercluster, our local supercluster, the gravitational neighbourhood of the Milky Way, is 520 million light-years across and contains the mass of 100 million billion suns. It is itself a small feature of the cosmic web. The cosmic web extends across the entire observable universe. The observable universe is, as we have discussed, a tiny fraction of the post-inflationary cosmos. In the post-inflationary cosmos is, if eternal inflation is correct, one bubble among an infinite number of bubbles in a multiverse that has no spatial or temporal boundary. At each step, the scale increases by a factor so large that all the previous scales become irrelevant. The distance to the nearest star is nothing compared to the distance to the nearest galaxy. The size of the galaxy is nothing compared to the size of the cosmic web. The size of the observable universe is nothing compared to the size of the post-inflationary cosmos. The post-inflationary cosmos is nothing compared to the multiverse. At each step, everything we thought of as vast becomes a negligible speck. And yet, we are here. You are here, reading this, or watching this, a collection of atoms on a rocky planet, orbiting an ordinary star in an unremarkable galaxy, in one of 2 trillion galaxies in the observable universe, which is itself a tiny region of a much larger cosmos, which is itself one bubble in a multiverse. You are vanishingly small. You are located at a single point in a space so vast that no number can convey its scale. You are here for an instant, a few decades in a cosmos that has been evolving for 13.8 billion years and will continue evolving for far longer. And you are thinking about all of this. You have assembled, from the light that has reached this particular point in space over these particular years, a picture of the cosmos that extends 46 billion light years in every direction and includes the physics of the first 10 seconds. You have used the mathematics of general relativity and quantum field theory and statistical mechanics to probe the structure of space and time at scales from the Planck length to the Hubble radius. You have looked at the cosmic microwave background and seen the universe when it was 380,000 years old. You have detected gravitational waves, ripples in the fabric of space-time from black holes colliding a billion light years away. You have used the transit of a planet across the disk of a distant star to infer the presence of an atmosphere and measure its chemical composition. This is not a small thing. In a universe of almost inconceivable vastness, in a multiverse of almost inconceivable variety, the emergence of minds capable of understanding that vastness is, at minimum, remarkable. Whether it is rare or common across the cosmos, whether the 2 trillion galaxies of the observable universe contain many civilizations capable of asking these questions, or few, or perhaps only this one, we do not know. The question of life in the universe is genuinely unresolved. The Fermi paradox, the observation that the apparent prevalence of conditions suitable for life in the universe is in tension with the absence of any detected extraterrestrial civilization, remains one of the deepest open problems in all of the tourist science. But the fact of consciousness, the fact that matter has arranged itself here in a configuration that experiences and reflects and asks, is real, whatever its cosmic frequency. The journey beyond the observable universe is ultimately a journey into the question of what it means to exist in a cosmos that does not care about existence. The laws of physics are indifferent. Dark energy does not prefer inhabited universes. Gravity does not preferentially form stars around worlds that might develop life. The universe is not hostile to life. It is simply not oriented toward it. It is not oriented toward anything. It runs according to equations that have no preferred observer, no preferred location, no preferred outcome. And yet here we are, observers in an unobserved cosmos, using our brief tenure in this particular configuration of atoms to map the structure of all things and ask where the edges are. There are no edges. That is the answer. The observable universe has a horizon, but not an edge. The post-inflationary cosmos is vast, but perhaps finite. The multiverse, if it exists, may be genuinely infinite and eternal. At every scale, the universe exceeds whatever boundary the previous scale suggested. The journey does not end. The fog does not end. The light does not stop. The physics does not stop. And that is, when you really sit with it, not a comfortable thought, and not an uncomfortable one either. It is simply the largest fact there is. The universe is not the size of your imagination. It is larger than that. It is not the size of your numbers. It is larger than that too. It is not bounded by your ability to conceive it. It extends beyond conception, calmly and completely, in every direction, for a distance that makes the word distance itself seem inadequate. Beyond the observable universe, there is more universe, and beyond that, more. And if eternal inflation is correct, beyond even that, more universes, each enormous, each complete, each governed by its own specific set of physical laws, each containing or not containing whatever complexity its laws permit. The cosmos is not a thing we are inside. It is a thing that contains everything, including the very act of our trying to understand it. A small eddy of awareness in an infinite expanding space, turning to look at itself, finding that there is always more to see. Everything we have described so far, the expanding space, the cosmic horizon, inflation, the multiverse, has been a spatial exploration, a journey outward. But now we need to change direction, because understanding what lies beyond the observable universe requires not only asking where, but when. And the moment you begin asking that question, you come face to face with one of the deepest paradoxes in modern physics, the direction of time itself. The laws of physics are, with a few important exceptions, indifferent to the direction of time. If you play a video of one billiard ball striking another in reverse, the reverse version does not violate the laws of physics. If you run the equations of electromagnetism backward, you obtain mathematically valid solutions. The equations of gravity work perfectly in reverse. The equations of quantum mechanics, with a few nuanced exceptions, do not resist time reversal. And yet, in the macroscopic world, time clearly has a direction. The past is different from the future. Broken eggs do not spontaneously reassemble. Heat does not flow spontaneously from cold objects to hot ones. A gas does not spontaneously collect itself into one corner of a container. This asymmetry, the arrow of time, comes from the second law of thermodynamics. In a closed system, entropy never decreases. But why does entropy increase? This question is far deeper than it appears. The reason entropy increases is not that nature prefers to increase it. The real answer to why it increases lies in the initial conditions of the universe. The universe began in an extraordinarily low entropy state. The Big Bang started not as a vast space where matter could be in any possible arrangement, but in an extremely compressed, extremely homogeneous, extremely ordered configuration. And given the laws of physics, when you begin from a low entropy initial condition and move forward toward higher entropy futures, the vast majority of intermediate steps will have higher entropy than the previous one. The arrow of time is a reflection of the universe's initial conditions. The reason Wednesday is different from Tuesday is that among all the microscopic states consistent with Tuesday morning, the state that happened to be valid exists near an extraordinarily low entropy configuration. This says something profound about the beginning of the universe, and something particular about beyond the observable universe as well. If the Big Bang represents an extraordinarily low entropy initial condition, why should this be so? The universe demands that we know some explanation for this initial low entropy. The second law of thermodynamics tells us why entropy increases, but it does not answer the question of why the initial entropy was low in the first place. This question, sometimes associated with the Boltzmann brain paradox, has long disturbed physicists. Boltzmann's paradox works like this. In a large system, in thermal equilibrium, entropy occasionally drops spontaneously through a statistical fluctuation. The larger these fluctuations, the rarer their probability. The probability of a system as large as our observable universe spontaneously transitioning to a low entropy state is vanishingly small. But in perfect thermal equilibrium, given infinite time, such large fluctuations eventually occur. The paradox is this: a fluctuation large enough to produce our entire observable universe is statistically extraordinarily rare. But a fluctuation small enough to produce only a brain, with false memories fully consistent with the past, would be far less rare. If the universe started from scratch and was produced by a fluctuation, why are we not a small brain that spontaneously appeared with hallucinatory memories of a past, rather than a large universe with a real past? There is no answer to this, at least not within the thermodynamic framework. This suggests that the initial conditions of the Big Bang require a different explanation. Inflation helps partially in this context. Inflation makes the universe's early phase extremely flat and homogeneous, providing precisely what the Big Bang's initial conditions require. But if inflation itself requires a low entropy initial condition, we have only pushed the question one step back. What explains the low entropy initial value of the inflaton field? The question continues to deepen. But this tells us something critical about beyond the observable universe. The arrow of time, the direction in which entropy increases, is not universal. It does not point in the same direction everywhere. Consider a multiverse in which different bubbles have different initial conditions. Some bubbles begin with extremely low entropy starts, and the arrow of time points in the same direction as ours. Others may have different initial conditions, and the arrow of time, for an observer inside that bubble, may point in a different direction. Some theoretical frameworks even suggest that at the joining point of two bubbles, two regions can exist side by side, where the arrows of time point in exactly opposite directions. What this precisely means is a challenge to the human mind, and this constitutes one of the deepest speculative regions concerning the boundaries of the universe. For now, we must accept The direction of time may be a local phenomenon. This arrow, valid in our universe, may not hold in the same way beyond the observable universe. And this is a genuinely disturbing idea, because causality, the foundation of everything, the backbone of every explanation, depends on the direction of time. Beyond our observable universe, there may exist regions where causality operates differently from ours. These are internally consistent regions. They contain perfectly coherent physics by their own lights, but from our perspective, they're incomprehensible. Let us return to our ship and travel a little further. 10 trillion light years, 100 trillion light years. At these distances, we need to think more deeply about two great mysteries that shape the universe: dark matter and dark energy. Dark matter is a matter component whose gravitational effects we observe, but whose interaction with electromagnetic radiation we have not yet detected. When you measure the rotational speeds of stars in a galaxy, you find that instead of decreasing toward the edges, they remain constant, an observation implying the existence of far more matter beyond the visible mass of the galaxy. Matter is approximately 5 times the visible mass. It emits no light, absorbs no light, leaves no trace in any band of the electromagnetic spectrum. Yet it acts through gravity, forming a vast halo around galaxies, shaping the filament structure of the cosmic web, and determining the growth of large-scale structure in the universe. Dark energy is far more mysterious. This component of the universe's energy, comprising roughly 68% of the total energy content in the standard cosmological model today, does not dilute as space expands. While ordinary matter becomes less dense as the universe expands, this component, called the cosmological constant, has maintained its value per unit volume since space first began. As a result, as the universe expands, the total amount of dark energy increases, which accelerates the expansion ever faster. What can we say about dark matter and dark energy beyond the observable universe? The answer to the first question is relatively simple. We have every reason to expect dark matter to continue to exist in the same proportion, because the homogeneity created by inflation and the same fundamental physics governing large-scale structure applies everywhere. The filaments of the cosmic web continue beyond the observable universe with the same statistical pattern born from the same quantum fluctuations. The great dark matter clusters, the great voids, and the filament pattern between them continue indefinitely. The answer for dark energy is more nuanced. In the cosmological constant interpretation, the assumption that dark energy is a property of empty space, it should have the same value in whatever region of space you inhabit. But if dark energy is truly something of a field nature with a variable value, as in theoretical approaches called quintessence, then its value could differ across space. In that case, beyond our observable universe, there may be regions where the universal expansion is accelerating at different rates. In these regions beyond our observational access, the cosmological constant may be different, and the consequences would be profound. Galaxies would recede from each other at different rates. The filament structure of the cosmic web would organize at different scales. Stars would form and evolve at different speeds. This brings us back to a vital implication of multiverse theory. If eternal inflation is correct, different bubbles settle into different effective vacuum energies. In some, dark energy is so large that the universe expands so rapidly after the Big Bang that matter never collapses into galaxies before structure can form. In others, dark energy is negative and the universe will undergo a deep collapse before galaxies can form. The small but non-zero value of dark energy we observe, this strange, fine-tuned cosmological constant value is explained by many physicists through an anthropic argument. Among the values that permit galaxy formation, we necessarily observe one consistent with our existence, because larger values produce no observers. This debate is unresolved. It may never be fully resolved, because there is no way to directly test the existence of other bubbles. But the point is this debate is fundamentally about what lies beyond our observable universe. The laws of physics we observe, including the value of dark energy, may differ out there, and that difference would not have occurred by chance, but would flow directly from the physics preceding the Big Bang. Our ship is now a traveller, not just in space, but in time. To go beyond the physical horizon, we must account not only for what exists far away, but what happens at very far future times. Because the observable universe as it is today will not always be so, and how that change unfolds contributes profoundly to our understanding of what the universe actually is. Let us go very far. 1 trillion years. Today, the universe is 13.8 billion years old. Star formation is still active. New stars are being born each year in the Milky Way. Galaxies are merging, and these mergers trigger new waves of star formation. The observable universe is full of bright galaxies. The filaments of the cosmic web light up occasionally. Quasars and active galactic nuclei illuminate the cosmic background, particularly in the early universe. But this situation is not permanent. The raw material for star formation, gas and dust, is being slowly consumed. Stars form from gas clouds. Gas clouds are depleted by various means, and replenishment is limited. Within a few trillion years, star formation will have practically ceased. The last stars, red dwarfs, extremely low mass and burning their combustible fuel with extreme care, dim reddish points, will live for trillions of years. While stars like the Sun last for billions of years, the smallest red dwarf stars will live for tens of trillions of years. Yet they too will eventually exhaust their fuel and transform into dim white dwarfs, then into black dwarfs. This period, extending to roughly 100 trillion years from now, marks the end of what is known as the stellar Jurassic era. After this comes a long, cold and dark age. The universe is illuminated no longer by starlight, but by the faint radiation of neutron stars and black holes ejected from the gravitational channels of great galaxies. Most planets will be slowly flung from their orbits or swallowed into central black holes. Galaxies will fragment through proton decay. If protons turn out to be unstable, as certain grand unified theories predict, this process will take approximately 10 to the power of 40 years. Beyond this, across a time span extending from 10 to the 67th to 10 to the 100th years, even black holes will evaporate. Hawking radiation, a process predicted by Stephen Hawking in 1974, causes a black hole to radiate at a temperature and thus slowly lose mass. For the most massive black holes, this process is extraordinarily slow, far longer than the current age of the universe. But given sufficient time, even the most enormous black holes completely evaporate, leaving behind only photons and other elementary particles. Beyond 10 to the 100th years, a number whose size challenges even the vocabulary of mathematics, the universe will continue to exist as a near-perfectly homogeneous, extremely cold, extremely sparse totality, consisting of low-energy photon and neutrino gas, devoid of any structure. In the presence of the cosmological constant, this state is not an infinite equilibrium. A possible existence might end through some final, theoretical quantum transition, or it might continue forever. The precise answer is unknown. What does all this far future contemplation have to do with what we were trying to understand before? The question of what lies beyond the observable universe. Here is the critical connection. The final state the universe reaches is a summary of its initial conditions and all the physical processes in between. The value of the cosmological constant determines the future. Whether protons are unstable determines the structure of the universe 100 trillion years from now. The measurements we make about dark energy today determine how the universe will look 10 million trillion years from now. And if the value of dark energy differs beyond our observable universe, if it differs in other bubbles, the future of those bubbles is entirely different from ours. While ours undergoes the long, slow cooling in which the last stars gradually go dark, black holes slowly evaporate, and nothing remains but light and quantum vibrations. One of those other bubbles may perhaps be heading toward the Big Crunch, an end in which matter collapses in on itself, in a universe where dark energy is negative. Another may be progressing toward the Big Rip, where dark energy is so enormous that galaxies, then stars, then atoms, and eventually the fabric of space-time itself tears apart. The beyond of the observable universe is not merely a continuation of everything that currently exists. It is also the site of all possible futures. Throughout everything we have described, we have touched on quantum mechanics repeatedly. Quantum fluctuations during inflation, the state of the early universe, the instability of protons. But now we need to address quantum mechanics more directly, because the question of what lies beyond the observable universe is deeply connected with how quantum mechanics must be interpreted at universal scales. Quantum mechanics is the system of equations that governs the subatomic world. It says that particles are not defined by specific positions and velocities, but by a probability wave called a wave function. An electron does not exist in a specific place until measured. It is in a superposition simultaneously in many possible places. When a measurement is made, the electron appears at a single location. First, one measurement is known as assumption X. This is how the world actually works, confirmed by experiment many thousands of times since the beginning of the 20th century. But the interpretation of quantum mechanics, how events actually unfold, remains contested. Does collapse physically happen in any real sense? Or, as in the many worlds interpretation of quantum mechanics, does the wave function never collapse and the universe branch at the moment of measurement? And this debate intersects with the question of what lies beyond the observable universe in a surprising way. The quantum state of the universe, the cosmological wave function, must encompass not just our observable universe, but all possible universe configurations. The Hartley-Hawking no-boundary proposal attempts to define this cosmological wave function mathematically. If the wave function of the universe is correct, then our observable universe is only one branch of that wave function. Other branches also exist. Universes with different physical constants, universes with different initial contentions, universes with different amounts of matter and energy, all existing as different components of the same great cosmological wave function. The difference from the many worlds interpretation is this. In many worlds, branching is local and continuous. Every quantum measurement produces new branches. In the cosmological wave function interpretation, branching occurs at the beginning of the universe, and each branch exists in its own completeness, with its own Big Bang, its own galaxies and stars and chemistry. This is the quantum version of the inflationary multiverse. This picture is highly speculative, and extremely difficult to test. But if you take the cosmological wave function idea seriously, the question, what lies beyond the observable universe, takes on a far deeper dimension. The beyond is not only spatial, it also encompasses branches different from ours in Hilbert space, the mathematical space of all possible quantum states. These branches are there. They exist mathematically, but they cannot physically interact with us. We can never reach them. We can never receive signals from them. Their existence follows from mathematical necessity, not from physical accessibility. In this context, the concept of observable takes on a new meaning. Our observable universe is not limited only to the region of space that light can reach. From the perspective of quantum mechanics, observable things are those that lie on a historical line consistent with us. A universe in another quantum branch may be just as real as a galaxy on the other side of the world, but because it can never interact with us, it is not out there in any practically meaningful sense. There is a question we have been avoiding since the very beginning of this journey. We described the magnitude of the cosmos, the number of galaxies, the number of stars, the vastness of space-time. But we have not directly addressed how common mind is within this vastness. We must do so now, because this question, is consciousness common in the cosmos or rare, is inextricably linked with the question of what lies beyond the observable universe. The numbers are astonishing. The observable universe contains 2 trillion galaxies. Each galaxy contains on average 100 billion stars. Current estimates show that billions of stars in the Milky Way have planetary systems, and in a significant fraction of these systems, there are solid surfaced planets in the habitable zone, close enough, but not too close, to their stars. These are numbers only for the Milky Way. When you account for 2 trillion galaxies, there are astronomically many potentially habitable planets in our observable universe alone. So why have we not yet detected any extraterrestrial civilization? This question, the Fermi paradox, is the famous question Nobel laureate Enrico Fermi posed at lunch in 1950, though its intellectual roots go much deeper. If life is common in the cosmos, and intelligence is common, and technology is common, then accounting for the age and size of our galaxy, at least one civilization should have had enough time by now to spread across the entire galaxy. Even travelling at only 1% of the speed of light, filling the galaxy would take only a few 100 million years, far less than the age of the universe, or even of Earth. And yet our galaxy, viewed with all the instruments at our disposal, is silent. There is no definitive trace of the existence of alien civilization. The solutions to the Fermi paradox form a spectrum. At one end sits the rare Earth hypothesis. Evolution leads to intelligence quite rarely. Complex multicellular life requires extraordinarily rare conditions. A moon of a certain size, a certain ratio of continental to ocean surface, the geodynamic shielding of domesticated giant planets, the star positioned in the galactic life belt. By this view, intelligent life may be far rarer than we believe, and perhaps we are unique, or nearly unique, within the observable universe. At the other end sit various hypotheses implying that the universe is full of minds, but these minds either cannot reach us or see no reason to communicate with us. From the perspective of what lies beyond the observable universe, this question acquires a new dimension. If the universe truly extends broadly, if space continues as a homogeneous medium to infinity, and physics is the same everywhere, and no matter how rare life is, it must occur again. However small the probability that all the conditions necessary for life on a planet would coincide in the form of an organism, the next similar planetary system is that much farther away. But if space truly encompasses infinity, that distance will eventually be filled. In a truly infinite flat universe, everything that can exist eventually does exist and occurs an infinite number of times. This brings us back to the copies argument we touched on earlier. In an infinite universe, there are not only infinite copies of you, there are copies of our planet, copies of our civilization, copies reading this text, all approximately 10 to the power of 10 to the 29th meters away. The deep meaning of this is, in an infinite universe, the concept of loneliness loses its meaning. If the universe is truly infinite and life can occur, we are not alone in the cosmos. We are not even separated from the infinite crowd of copies by so much as a quantum vacuum fluctuation. Whether this idea is mind-opening or comforting or overwhelming is for you to decide. The answer physics can give you is ambiguous. We will go further, but first we must stop and ask something utterly fundamental. How much information can exist in space? We must ask whether the true boundary of what lies beyond the observable universe is set by the amount of information that can be stored and transmitted. The holographic principle is one of the deepest and most disturbing ideas in physics. Arising from the work of Jacob Bekenstein and Stephen Hawking on black hole thermodynamics, it contends that the maximum entropy, and thus maximum information, in a region is determined not by the region's mass, but by the area of its boundary. After showing that the entropy of black holes is proportional to their surface area, physicists began to think that this principle applies not just to black holes, but to all spatial regions in general. If you fill a system completely with information, that system becomes a black hole. This shows that the information capacity of a region is bounded by its area. If this principle is correct, and it has strong support in the context of string theory and quantum gravity, some extremely strange consequences follow. The total amount of information contained in our observable universe can be expressed as a number with a certain computational capacity per second. This number is large, immensely large, but finite. Somewhere on the order of 10 to the power of 10 to the 123 bits. What does this say about beyond the observable universe? The holographic principle contends that all the information about the region one sees is encoded on the boundary surface of that region. Does this really mean the universe is two-dimensional rather than three-dimensional? Physicists disagree at this point, but if the holographic principle is literally correct, then some or all of the information about what lies beyond our observable horizon may already be encoded on our own horizon surfaces. Observing more of the universe beyond may be impossible as a matter of principle. This line of reasoning could fundamentally change our idea of travel in linear space. Perhaps going outward does not yield new information about what lies beyond. Perhaps every observation point contains exactly as much information about the rest of the universe as is available right there. Going farther does not reveal more detail. It reorganizes the same information from a different perspective. This may appear to be metaphysical speculation, but it is not entirely so. The holographic principle took concrete mathematical form with the ADS-CFT correspondence discovered by Juan Maldacena in the 1990s. This correspondence showed that a theory of gravity in a certain variety of space-time is fully equivalent to a quantum field theory living on the boundary of that space-time. This is a holographic reality predicted by mathematics. Whether our real universe has this kind of holographic dual structure is not yet known. ADS-CTT concerns curved space and the real universe is flat, but the possibility is being seriously considered. Viewed from this perspective on what lies beyond the observable universe, the concept of beyond itself becomes questionable. If all information is already encoded on surfaces available to us, what does beyond mean? That answer cannot yet be known, but the question is real. We have looked at very large scales. Now we will look at very small scales. And these two extremes may be connected to each other far more deeply than we suppose. Space and time appear to be a seamless, continuous fabric. It seems as if any distance could theoretically be halved again, divided indefinitely. But this cannot be right, because in continuous space, it would mean any 2 points could be infinitely close, implying infinite energy density, where quantum mechanics and general relativity are simultaneously valid. The theory of quantum gravity suggests that space cannot be meaningfully divided at the Planck length, approximately 10 to the minus 35 meters. This does not mean space is discrete in the manner of a grid. Rather, it means the same lengths have a possible minimum meaningful value. Loop quantum gravity contends that at the Planck scale, space-time truly has a discrete structure and consists of combinatorial structures. These networks constitute geometry. Space is not something that takes shape at points bearing field values. Rather, it exists as an abstract network of nodes and connections. Each node of this network defines a region, and each connection defines the area of the boundary between those regions. If this view is correct, the question of what lies beyond the observable universe takes on an unexpected dimension. The fabric of space-time may consist of countable discrete structures. Going far enough, the question of how the properties of these structures continue becomes meaningful. If information is only measurable by surface area, and this surface area is expressed in discrete Planck units, then the infinite space beyond truly contains infinite discrete units. This helps to eliminate some of the purely mathematical difficulties concerning infinity, but brings new ones. Even more deeply, if space-time is discrete and structured at the Planck scale, the concept of infinite universe becomes suspect. Something consisting of an infinite number of discrete units can be mathematically infinite. But this is different from the infinity of a continuous space. Topology, metric, continuity, connectivity, all of these may need reinterpretation at the Planck scale. And this reinterpretation fundamentally affects the structure of what lies beyond the observable universe. This is not a partial answer, but an open question. Loop quantum gravity is not yet complete. Experimental predictions have not yet yielded definitive results. But the Planck scale discussions form a profoundly deep bridge connecting the question tabion by tab. What is the beyond of the universe like? To the question, what is space-time fundamentally? This entire journey, expanding horizons, dark energy, inflation, multiverse, quantum gravity, entropy, and the hour of time, ultimately leads you to an unavoidable question. Why does the universe exist? Why is there something rather than nothing? Whether this question belongs to philosophy or to physics is debatable. Many physicists find the question meaningless, at least as a question science can answer. Physics describes how events develop from the current state. The question, why does it exist, lies outside this framework. Even quantum mechanics does not claim that empty space is less than nothing. Vacuum energy, quantum fields, and the topology of space already exist. Vilenkin's tunneling from nothing proposal is a proposal with mathematics behind it, but even the nothing here is a mathematically defined concept. not truly nothing in any ordinary sense. Leibniz formulated the question as, why is there something rather than nothing? For Leibniz, the answer was God. For modern physicists, the answer is either the question is meaningless, or we don't know, or, as the most honest reply, perhaps it cannot be answered. If the laws of physics necessarily require certain conditions for existence, and these laws arise from necessity rather than chance, then perhaps the question, why does it exist, has a self-answering structure. Some mathematicians and physicists contend that the universe represents a kind of Tegmark multiverse, in which everything that is mathematically possible exists. In this approach, the question why something rather than nothing becomes meaningless. Every mathematically consistent structure exists in some sense, and we simply exist as conscious beings within the structure we happen to inhabit. None of these views has definitive proof. None is testable. But they are not empty speculations either. They are the products of serious efforts by physicists extrapolating from available theoretical frameworks. And this question's direct relevance to beyond the observable universe is this. If the universe arises from an existential necessity, that is the real answer to the why does it exist question. Meaning, if existence itself is necessary and nihilism is impossible, then beyond the observable universe is not merely more space, it is a manifestation of the necessity of existence. If nothing is impossible, everything that exists from necessity. And if everything that exists from necessity, beyond the observable universe exists with the same necessity, without any additional condition. This brings us to the final and deepest point of our journey, an inquiry into the meaning of existence itself. Our ship is now very far away. We are billions of light years from our starting point, that small, blue, water-covered planet orbiting that star. Wherever we look, galaxies, dark matter, the filaments in voids of the cosmic web, the same physics, the same beauty, and the same indifference. The fact that the cosmos is indifferent to us is one of the oldest and most disturbing discoveries in human history. The universe produced conscious life without intending to. The first blow came when we learned that the sun revolving around the Earth was not the centre of the universe. The second came when we learned our galaxy was a typical galaxy, our sun a typical star, the Earth a typical planet. The multiverse, made possible by cosmic inflation, delivers the final blow. It renders us not merely off-centre in the universe, but a momentary configuration and a corner of one bubble among an infinite number of bubbles. And yet, here we are. You are reading this sentence. You are understanding something. More than that, you are feeling something. Curiosity, wonder, perhaps a mild vertigo. These feelings are real. This curiosity is real. And knowing that this curiosity is the product of 13.8 billion years of cosmic history, the product of a long and blind process in which hydrogen transformed into heavy elements, these elements joined planetary structures. These structures passed through millions of years of evolutionary processes, and the atoms living within them finally became entities questioning one another, does not make it less real. Meaning is not woven into the fabric of the cosmos. For many people who know this, it is a great source of loneliness and purposelessness. But another framework is also possible. If meaning is not woven into the fabric of the cosmos, then we, the only beings who produce meaning, are its distinctive feature. Giving meaning, experiencing, understanding, marveling, loving, none of these exist in the rest of the cosmos. Most of what exists in space is the silent dance of matter and energy unaware of itself. The rare corners aware of this dance, life, consciousness, understanding, are somehow different. How different? We do not know. How many other loci of consciousness exist beyond our observable universe remains unknown. Perhaps only 1 per billion galaxies in the universe, perhaps 1 per star, perhaps, according to one possible answer to the Fermi paradox, we are truly singular and may be alone among knowns in the entirety of the observable universe. This possibility, as disturbing as it is, may also imply a great responsibility. And here, at the very centre of the meaning discussion, all our cosmological thinking about beyond the observable universe arrives at a particular focal point. Even if the universe is full of unknowable voids where consciousness has never flickered, the act of understanding itself, that moment when matter looks at the structure of the universe and becomes aware of its own existence, is the universe comprehending itself. The act of understanding, however partial and flawed, is a kind of symmetry breaking in which matter itself is experienced. Without us, the universe would be an endless performance in which stars are born and die, galaxies form and scatter, black holes grow and evaporate. Nothing would lose its meaning because there was no meaning in the first place. When we exist, meaning becomes possible. That is all, and that is genuinely enough. You took your ship beyond the universe. You travelled from bubble to bubble, through eternal inflation, then into other bubbles. You saw how quantum fluctuations shape the filaments of the cosmic web. You understood that no physical connection to other universes is possible. You thought about the arrow of time and why entropy increases. You saw what the holographic principle says about the limits of information and what the Planck scale says about the true structure of space-time. You examined the question of consciousness and the question of meaning. And now you are left with a single question. Is this all there is? No, certainly not. Because every answer gave rise to new questions. Why were the initial conditions this way? Why did the inflaton field exist? Why did the physics that allowed more than one bubble exist? What is the true ontology of quantum mechanics? Does the wave function really collapse? Or does the universe's quantum gravity actually work? Is the holographic principle fundamental or derived? None of these questions can be definitively answered today, and this is not a sign of failure, but of progress. Each generation has replaced the questions answered by the previous generation with deeper ones. Newton described gravity. Einstein brought a deeper geometric explanation of why this should be so. Today's physicists are trying to characterize Einstein's theory under conditions where it loses its validity at the Planck scale. At each step, the universe turned out richer, more complex, more unexpected. Is there an end to this process? Is there a single, final theory that completely explains the laws of physics, all of nature, existence itself? Some physicists believe there is, the theory of everything. Others think it is not possible, for a reason analogous to Gödel's incompleteness theorem about integers. No consistent system of theories can prove all the truths within itself. Physics, if it becomes rich enough, may run into its own boundaries. But even these limits are a kind of answer. If physics can discover its own limits, that is already an extraordinary achievement. Finite-lived beings, living in a small corner of the great universe, can express the limits of space-time in mathematical propositions. This is truly extraordinary. Your ship is returning now. After the long journey, after having travelled billions of light years away, after having imagined the boundaries of the multiverse, after thinking about the arrow of time, after addressing the question of consciousness, you are returning to your corner of the observable universe, to the Milky Way, to the solar system, to this small rocky planet, What have you brought back with you? First, perspective. The urgency of daily existence, deadlines that need to be met today, grievances, anxieties, genuinely diminishes. If you truly internalize the dimensions of the cosmos, nothing feels the same. This diminishment is not painful, but liberating. No individual concern carries cosmic significance, and this, paradoxically, makes every individual moment more valuable. If meaning is not woven into the fabric of the universe, and we produce it, then every moment is the place where meaning itself is being produced. Second, humility. We know great things. We know the universe is expanding, that the Big Bang occurred, that the cosmic microwave background radiation exists, that inflation solved the problems, that dark energy is accelerating the expansion. But there is far more we do not know. We do not know precisely what dark matter is. We do not know which theory of quantum gravity is correct. We do not know whether the multiverse truly exists. We do not know how rare conscious life is in the cosmos. We do not even know with certainty whether time truly exists. Some theoretical frameworks treat it as a derived concept. Third, curiosity. The most valuable thing, not the journey itself, but the curiosity that makes the journey possible. The universe did not exist to be understood. Stars did not ignite to be admired. Galaxies did not take shape to be discovered. And yet, here, on this small rock, beings formed from atoms are asking questions. This curiosity does not change the universe. It does not stop the sun from burning, does not shrink black holes, does not delay the Big Rip or the Big Freeze. But it changes the beings within whom it occurs. A cluster of atoms that wonders is different from a cluster of atoms that does not. This difference is small, insignificant on the cosmic scale, and it is real. The ultimate answer to the question of what lies beyond the observable universe is this: more universe, more time, more structure and void, more stars and darkness, more unknowing. And perhaps, only perhaps, it is not possible to know this with certainty. More curious beings, more consciousness, more meaning-making, more asking of great questions and giving of incomplete answers. More of this extraordinarily strange process, matter attempting to understand itself. The beyond of the horizon is like a mirror. When you look into it, what you see is not something living beyond space and time. It is a reflection of something living here. The immensity of the cosmos does not measure the smallness of yourself, but the greatness of understanding. And this understanding, partial, flawed, continuously revised, never complete, is humanity's best answer to the cosmos. The fog does not end, the light does not stop, the physics does not stop, the questions do not stop. And this is perhaps the most beautiful thing that exists in the entire universe.